So, welcome to module 4.2, the hack microarchitecture. The expectations of the hack microarchitecture has been set forth in the module 5.1, wherein we said that it had to do 5 operations for every instruction. So, the PC, the program counter will point to some instruction in the instruction memory and it has to fetch it, decode it, fetch the relevant data, execute the instruction, store back the results and then go to the next instruction. And by the time the PC will also get updated with what should be the next instruction. The next instruction can be the instruction that is following it, in which case the PC is incremented, or it can be some other instruction as in the case of a control transfer instruction like a conditional jump or an unconditional jump. In that case the PC will get the value, the address of the next instruction from the A register. So, to this level of detail we have finished off in module 5.1, and if you have any doubts please do raise it up in the discussion forum and we can address this. So, what we will do in this module 5.2 is we will now go, so there are 2 classes of instruction, namely the A and C instructions, and that has to be executed by the hack microarchitecture. So, how do we build this microarchitecture from the basic combinational and sequential circuits that we have built as a part of project 1, 2 and 3. So, that is where we are going to take up. So, this is the context of what you are doing. So, I will be using a set of slides for this to explain. So, we want to understand the hack microarchitecture and its functioning, and the best way to learn this is by an example, right. So, we will take a C code, we will take its equivalent mnemonic code, right, and then we will basically go and do the next step of how the mnemonic is getting translated into machine, that we have seen as a part of your module 3, and once that machine language is available, the zeros and ones are available, how does the the architecture takes those zeros and ones and carries out the necessary action. So, that part we need to understand, and for that we will be using a set of slides. Now, the simplest example I am going to take to explain you the entire hack microarchitecture is one which will find the maximum of 2 numbers A and B. Look at the C program that we have on the side of this. So, there is a word main int A comma B, C is max. I make A is 11, I make B equal to 20, I make C equal to B minus A. If C is less than 0, then max is A, else max is B, right. So, this is a very simple program which will find the the maximum of A and B. Now, how do we do this, right? Now, we assume there are 24 instructions. This will essentially get transformed into 24 instructions, and those are as follows. First thing is the first instruction, first translation would be at A equal to 11. So, what we are doing here, we are basically these 2 instructions will tell you what do you mean by this at A equal to 11. So, at 11 D equal to A. So, the register D, as such our microarchitecture has 2 registers, D register and A register. So, the register D will basically take the value 11, right. Now, let us assume that A is stored somewhere. So, at A is the address of A, this is the address of A. M equal to D. So, now A becomes 11. So, M means M of whatever is stored in the address register, that will now become D, D is 11. This is what M equal to D means, right. So, when I say at A, the address of A is loaded into the capital A register, and the moment I say M equal to D, that M of A now becomes 11. That means the variable A gets a value 11, A equal to 11 is completed. Similarly, at 20, now D becomes 20. Now, at B, this is the address of B. Now, M equal to D, that means B equal to 20 is finished. Okay. So A equal to 11 is done by the first 4 instructions, B equal to 20 is done by the second 4 instructions. Sorry. B equal to 20 is done by the second 4 instructions. Now I have to do C equal to B minus A, right. C is a temporary variable for me, so I will not I don't need a location, explicit memory location for C. So the way I am compiling it is at A, again I go to the location A and I say D equal to D minus M. What is D here? D is storing the value of B here. As such, D is storing the value of B. Now again I say at A, so in the capital A register the address of small a will be loaded. Now I say D equal to D minus M, that means now D will be storing B minus A, because M now will get the value of small a, because the address that is there in the capital A register is that of small a. So M will get the value of small a. So now D equal to B minus A. Now I am putting a label at A max. The label here is A max. Now D j less than, if D is currently storing B minus A, this JLT essentially says that if the result is less than 0, take a jump. So if B minus A is less than 0, that is C is less than 0, I go to A max, right. Otherwise I start doing these set of instructions. What are these instructions doing? First at B, so D will now become B. Now at max, right. So max is the memory location for max, right. So M equal to D, so M equal to D means M gets the value B, that means max is equal to B, because the address now points to max. So when I say M equal to B, so max gets the value B. Now at end is a label which is given here. I 0 colon jump, this is an unconditional jump, so I go and jump to this end, and then this is an infinite loop, just to say that I have finished. I will just be looping here. So if your B minus A is greater than or equal to 0, then your max is equal to B, that is what we are doing. If C is greater than or equal to 0, C is B minus A, greater than or equal to 0, then max is equal to B, else max is equal to A. So this A max, the same thing at A, D equal to M. So D gets the value of A, because at A loads the address of A to the capital A register. So when I say M, so I get the value of small a, and so at max M equal to D. So again these two instructions, as you see, will make M is equal to A. So when B minus A is less than 0, max, when B minus A is less than 0, max is A, otherwise max is B, then it will come to this hand and jump. So the C code that you see on the left hand side essentially gets translated to this hack mnemonics, right. I just redid this just for you to recap, because we have done it as a part of module 3 end, but I am just doing this as a recap so that it reinforces your understanding of the mnemonics and its equivalent high level language programming construct. Now what we do now this is what the corresponding machine instruction would be. So the mnemonic essentially becomes this machine instructions. So the translation from the mnemonic to the machine instruction is done by the assembler. Okay, we will deal about, we understood what assembler is, but how the real assembler is constructed we will see in the subsequent modules. Now these are the instructions. So there are 24 instructions. So this those are being stored in the memory from 0 to 23. So, this is the instruction memory as you see here, this is the instruction memory. So, the instructions are stored from 0 to 23. So, at 11 is a instruction. So, the first bit is 0 and the remaining bits if you see it gives you 1011 which is 11. D equal to A, this is a C instruction, the first 3 bits are 1s, right, and then we go back to module 3 to understand that the A bit should be 0. When the A bit is 0, then basically these are the 110000, these are the bits that are needed for for the computation by the ALU. So, this will correspond to your ZX, NX, ZY, NY, Z, FO, the functionality and NO, F and NO. So, these are the 6 computation bits. 010 is the destination bit and 010 essentially says that your destination is D if you go and look back, and this is not a jump instruction, that is the last 3 zeros. So, the D equal to A essentially gets translated to this. Now, at A again this is an A instruction which is 0, and let us assume that A is stored in address A, B and max are stored at address 16, 17 and 18 in the data memory. The 16, 17 and 18 in the instruction memory is occupied by these instructions, 16, 17 and 18 in data memory is occupied by A, B and max. Okay. So, when I say at A, it means that A is stored at 16. So, this is 0 and when you look at the remaining things, this corresponds to the decimal value 16, 10000. Now, I am saying M equal to D, again this is a C instruction, so the first 3 bits are here. This A basically decides that the source operand is D and 001100 are the corresponding computation bits, and then these 3001 essentially says that the destination is M, and then this says it is not a jump, last 3 zeros says that it is not a jump instruction. Now, again at 20 this is an A instruction, and this is when you see 10100, this is 16 plus 4 20, this is a decimal binary equivalent of 20. D equal to A, this is a C instruction. This bit 0 bit essentially says that this is the operand A. 110000 essentially gives you the computation bits. 010 is the destination, which says the destination should be D, and then this is not a jump instruction. Now, at B, note that B is stored at 17. So, this is an A instruction. So, this is 0 and the remaining thing corresponds to 17. Now, M equal to D, this is a C instruction, again 111. This 0 bit will tell you about the destination operand, that is D. 001100 is the computation bits. 001 is basically the destination, which says destination is M, and then 000 is a jump. You can also refer to the table that we have introduced in the module 3 and in the book, which gives you a combination of A and the computation bits for A0 and C1, C2, C3 till C6 be some value, then the corresponding operation that will happen. And then there is also a table that we have introduced wherein your the destination bits depending on the 3 bits, destination bits, where what is the corresponding, is it M or D, what is the destination. And also there is a table which says that 7 different possible jumps, okay, which corresponds to the last 3 bits. So, this we have already taught. So, just go back and have the table at your side, so that this you can understand this much better, right. Now, next is at A. So, this is A instruction and A is stored at 16. So, you get 16 here. D equal to D minus M. So, this is a C instruction, this is the A which says A is 1 and the computation bits are 0 1 0 0 1 1, then the answer will be D minus M, and then you have the 0 1 0 0 0 1 0, which basically says that your destination is D and this is not a jump. Now, at A max, okay, this is something that we need to understand. So, what is A max? A max actually resolves to this location, which is 18, right. A max is a symbol which is associated with the address number 18, right. That who will resolve that. So, essentially what this is an A instruction. So, 0, this is 18. If you take this set of bits, this is now 18, 1 0 0 1 0. Who will resolve this for you? This will be resolved by the assembler. The assembler is responsible. So, the assembler will first scan this, it will do one passes from end to end of the previous thing that we see. So, this will do a one pass of this and find out that A max is going to be 18, and similarly end is going to be 22. So, for all the symbols that we have used here, namely A max and N, it will find out what is the corresponding binary value, because these things basically point to addresses. So, it will find out which address it is mapping to. So, at A max, now it knows that it is 18, then D JLT. So, this is a C instruction. So, first 1 1 1, this is 0, essentially says the destination source operand here. 0 0 1 1 0 0 essentially says that you are going to come, the output of the ALU will be D. If A bit is 0 and the C bits are 0 0 1 1 0 0, the output of ALU will be D, and there is no destination here because the jump instruction, and the jumps are 1 0 0, which essentially says that I want to do a JLT, jump meant less than. Okay, this is there. There is a jump table, right, 7 different jumps and what are their encodings. So, 1 0 0 corresponds to JLT, right. Now, again at B, D equal to M, at max. So, we said that the max is at location 18. So, this will come 18, M equal to D. Again here at end resolves to 22 by the 2 pass assembly. So, 22 will be loaded here, 1 0 1 1 0, this is an A instruction, and then 0 colon jump and all these things. Okay. So, essentially this is how your this is the interpretation. Why we went through this interpretation is because we need to have an understanding of how the machine instruction has to be interpreted by the architecture. So, the interpretation that we have seen now, once this machine code of zeros and ones is presented to the architecture, the way we have interpreted in English, the circuit has to interpret and carry out the necessary action, and that is the essential crux of design of an architecture, right. Now, in the next module, that is 4.3, we will go and see how the architecture basically takes these bits and interprets it, and how do they resolve the issues. Before we conclude, this is the proposed implementation of the topmost computer hack chip. So, the topmost computer hack chip will have an instruction memory, will have a CPU, and will have data memory, right. So, it will have instruction memory, it will have CPU, it will have data memory, right. Now and the CPU will have a program counter internal to the CPU. The program counter will send its address, the program counter will send its address to the ROM, the instruction memory. That instruction will come here, right. That instruction, when it is executing, it will ask for a read or write into memory, this is the write m. So, this will be used for read or write, and this is the address, and if it is a write operation, the data will come in out m. If it is a read operation and write operation, data will come in out m, and this write will become 1, and this will be the address. So, if write is 1, out m is data, then address m is the address. So, in this address the data will be written. If write m is 0, then out m is not used, it is do not care, and address m. So, you read from this address back. So, the output of this data memory essentially comes back, the output, there is one output of the data memory which will come back to the CPU. That is when I read, when the CPU reads some value from the memory, that thing has to come from this part. So, this is how the data memory and instruction memory and the CPU works. The CPU essentially has certain sequential component like a register and PC. There are two registers, D and A, and a PC. These are the three sequential components inside the CPU, and all the remaining things that we see, inside the CPU are combinational elements, and we will be using the ALU, we will be using many things. So, this is how this is the proposed implementation. To sum up, I will sum up this part. There is a CPU, there is a PC. That PC basically gives the address of the next instruction. Based on that PC, the instruction memory in a tick of a clock basically gives you the CPU address, and in this CPU, so we have write m, out m and address m. So, you give a particular address and write m is 0, and your then this data memory will read the particular address and give back the content of that address through in m, which will come to the CPU. When the CPU has to write something into the memory, that will be the end of that operation. It will make write m as 1, and it will put whatever it wants to write on the out m bus and the address in address m. So, the data memory essentially gets updated. So, this is the proposed architecture of hack, and we will continue more on this as we proceed through the next steps. Thank you.